Hi, thank you. It's good to see you all. Hope you guys have been enjoying the time here. I know I've been looking forward to it because I'm really excited to talk to you all today about something that's been occupying my mind a lot over the last couple of years. And that's how we power the devices that drive our world. When I talk about powering a device, whether it be the mobile phone in your pocket, the electric vehicle driving down the highway out there, or moving ahead to the robotics and drones of the future, you're probably thinking of exactly the same thing in each of them: a battery. Now, while the devices themselves have changed a lot over prior decades, the battery hasn't changed a lot in the last 225 years. Minor changes have happened, but it still very much resembles the voltaic pile that Alessandro Volta debuted in 1800. It's still a rigid series of anodes and cathodes in a row, not too dissimilar from the artillery formations after which it gets its name. But what if it didn't have to be that way? What if we were able to make a power source that is agnostic to the use case? What would that look like? How could that be used? While you think on that, I'm going to kind of give you an idea of how I reached this question and what my thoughts are on it, because we'll get back to that. I started this journey actually on a kind of smaller scale. I did my postdoc at the Army Research Lab, and I worked very closely doing metrology for the power and electronics branch there. I looked at wide bandgap semiconductors for power electronics. I looked at phosphors for power generation. And it taught me a lot about the needs of the dismounted soldier. We in MTO especially are very guilty of providing even more and more fantastical electronic devices that all require power to drive them. And so the power needs are only increasing, and they're only going to get worse. The average dismounted soldier today carries something like 20 pounds of batteries for a 3-day mission. That's huge. What's worse, it's in 7 different form factors, none of which can be used in any other system. There are ways of trying to solve this. You can go the route of trying to create one standard battery to rule them all. This is not a bad idea, but it does require you to either retrofit things that came before it or to design entirely new equipment and purchase it. And then there comes the question of how do you choose the characteristics that go into that. You could also create new standards that people can carry. You can create battery packs that people have to bring with them with charging cables that go into the batteries, et cetera, et cetera. Also, not a bad idea, but neither of these really kind of gets to the fundamental reason why, which is the fact that a AA can't fit where a CR123 is. So this got me thinking, what if we could arbitrarily change the size and shape of these batteries such that you could use it in any of the devices in the field? There's been a tremendous amount of work in 3-dimensional batteries. There have been some issues there. There's been a tremendous amount of work in flexible batteries, mostly 2-dimensional. What if we combined these two? What would that look like? So we talk about the current mission, current failings of gear. Let's think about what else we could do. What sorts of missions could we accomplish now if we have this malleable stuff, this pragma? Well, one of the examples I was thinking of is, let's say we've got a squad behind enemy lines. They are dealing with a medical emergency for one of their troops, and they need to get back to our lines quickly. There's no way of getting someone in there quickly enough to get them, and they come upon a disabled vehicle. Now, the engine still works, but the battery's dead. It's been left there for too long. Currently, there's no way of dealing with this. But if you've got something that's malleable, something where you can change the mass, perhaps, of this by combining it, and I know this sounds like sci-fi, but DARPA's where we make science fiction just science, so bear with me for now. But if you're able to combine this, perhaps think of it like C4 with wires or what have you. Maybe you can make a 12-volt battery that can give you the cold crank amps to start that engine and get your troop home. What's more important is that something like this would not require a rebuilding or a remanufacture of prior systems. It could fit in any of them. Similarly, you and I at home, when we have an electronic device where the proprietary battery in it goes bad, and the only way we could possibly get another battery for it is to purchase a lot of 10,000 from some seller on Alibaba, could simply just take some of this stuff and put it where it needs to be. And we can keep the things that we enjoy using, the things that are good and important in our lives, working, and end up with less waste. This isn't the whole story, though. What does this change about the way we design things moving forward? To that, I'd really like to draw your attention to the image on the right. We've taken some lessons from the Russo-Ukrainian war, and one of those has been the increased use of drone warfare. Small, Class 1 drones. Many of these commercial drones are not well equipped for the ranges or the carrying capacities that the soldiers out there are demanding of them. And some very enterprising companies have started to retrofit them. And as you can see there, that large blue pile, that's battery packs that have been put together for this. And what that is 6 18650 cells that you might find in an electric vehicle, all wired together, wrapped up together. It's 6 batteries in a trench coat. That still wastes a lot of space, though. A lot of that is packaging that isn't going towards energy, it's going towards a drain. What if instead you had a way of filling the crevices in that drone instead with your power? You've still got an aerodynamic platform. How would that change your designs going forward? How would a malleable battery that could fit in the A-pillar of a car or in the door change the way we design and build cars? No longer do you have that skateboard underneath it. No, instead, you're distributing it throughout. You've got control over aerodynamics. You've got control over balance. How does this change how we look at robotics? A lot of you, when you think, well, certainly when I think of a bipedal robot, I first think of the Boston Dynamics Atlas, which very famously had that big battery pack on its back. It's been moved inside since then, I know. But that's a very dense load that causes torque, it causes strain. You have to have the galvo motors and servos in there providing resistance against that, and that's power. What if you were able to distribute this energy throughout the robot? Think of it as taking a cue from the best in squishy energy management out there, us. You've got muscle here. It provides both the force and the energy. What if we took the lesson from that? Suddenly you can bend everything and you're not losing it. So what I've just described is a universal battery, though I think perhaps I've already convinced myself that we need to come up with a new name, because that's that rigid artillery formation. And what we want is a battery where you can arbitrarily change the size and the shape of it without sacrificing the things that we care a lot about, like energy density, like cost, like safety. This is going to be really hard. Because obviously, you can't just necessarily abandon the fact that you still need an anode and a cathode. You still need separation between them, a means of transmitting ions back and forth between them, an ability to collect the current coming out of it. And you've got to do all this without any rigid metals holding it together. You've got to do this such that your state of charge, your voltage are stable as you deform it. What use is a battery where when you put it in your device, it's already discharged? You've got to do this with materials that are stretchable and deformable in multiple different ways. And you've got to do this in a way where your interfaces maintain their cohesion. Otherwise, you're just going to end up with a pile of inert stuff. So how do we go about making these entirely new batteries? And we need to do it in such a way that we're able to leapfrog the current status. Because when it comes to battery manufacture, the United States is an also-ran. A lot of the incredible early technology has come out of here, but it has been offshored. It's been taken to places where you've got a large industrial facility where you are creating flat collections of anode and cathode and separator. And then it's going into specific places where you are die cutting things, rolling them together if it's cylindrical and what have you. But now, we get to think about new materials. We get to think about new manufacture methods. Now you're able to make one particular type of thing, one stuff, one battery, and have it go to anything you need it to. This eases supply lines, this eases logistics. It allows for factories where you're not necessarily trying to catch up with people who've been perfecting it and going after this one thing for decades. You've created something entirely new. This is also incredibly important because stable and reliable electrical power is necessary for national security, and this sort of work is necessary for our economic security as well. So here's where my ask to you comes in. How do you think we're going to go about doing this? I obviously have my own ideas, but I'm one person, and science isn't done by one person. It's done by a bunch of brilliant minds coming together and working together to come up with new ways of approaching a problem. Now, I'll start out and tell you what I don't want. As much as I enjoy the work that has gone on with flexible batteries, that's still thinking in a 2D world, and I don't think it scales enough. I'm very aware of it, and it's very cool stuff, but that's not what I'm looking for. Similarly, I don't want anything where it's going to hamper our design such that we have to either retrofit older systems or specifically design new systems to hold it. This means things like flow batteries and fuel cells, as much as I think that they are incredible and they have their place and they are the future in so many ways for so many different applications, are not what I'm looking for here. I don't want to have to worry about a holding tank. I don't want to have to worry about piping. I don't want to have to worry about an impeller pump. But what I do want is your ideas on new electrochemical pairs. I want your ideas on how we're going to manufacture these things. If you have ideas about the geometry of how these structures are going to get put together, if you have ideas on how we're going to get current out of it, how we're going to package it. And I think even more importantly, where am I being chained to tradition? What don't we need if we change this? Do we still need a separator? Do we still need an anode? Do we still need a cathode? Anolytes and catholytes exist now. Do we still even need packaging? Or have the packaging requirements changed so thoroughly that that's just a thing we don't have to worry about anymore? So with that, I look forward to hearing from you, and thank you very much for your attention.